Hello, I'm Koss Simons. This video is my deliverable for the Duke University Machine Learning Foundations for Product Manager's Coursera assignment. In the next 5 minutes, I'll show how 4 ambient sensors let us predict a combined cycle power plant's hourly output with less than 1% error. Here's the data we're modeling. We have 9,568 hourly records from a combined cycle power plant. Each row gives 4 ambient sensors: temperature from 1.8 to 37 degrees Celsius, exhaust vacuum 25 to 82 centimeters of mercury, ambient pressure 993 to 1,033 millibars, and relative humidity 26 to 100%, plus the target net power output, ranging 420 to 496 megawatts. In the correlation heat map, the 2 almost white squares jump out: temperature to power at minus 0.95 and vacuum to power at minus 0.87. White in this palette marks the strongest negative links, so hotter air and higher back pressure sharply reduce output. Because we're predicting a continuous number, this is supervised regression, and we'll score models with root mean squared error in megawatts, the plant's own units. With that data picture in mind, let's see how we turn these 4 sensors into a predictive model. Here's the game plan for the model. Inputs. We keep all 4 numeric sensors exactly as they are: temperature, exhaust vacuum, ambient pressure, and humidity. Nothing to encode or scale beyond standardizing for the linear model. 2 candidates. Multiple linear regression. One straight line through the data gives us a transparent baseline. Random forest, 200 trees, hundreds of small decision trees whose average can bend and twist to match non-linear patterns. 200 trees are enough for stability and still train in under a second. How we judge: root mean squared error in megawatts. Using the plant's own units makes every miss easy to interpret. Fair comparison. First, we park 20% of the rows as a blind test set. On the remaining 80%, we run 5-fold cross-validation. Each fold gets a turn as the validation slice, while the other 4 folds train. That gives 5 independent RMSE scores per model, average to decide the winner. Let's see which model comes out on top. Here are the cross-validation scores. 5 folds, same splits, 2 models. The linear baseline lands at 4.57 megawatts on average. The random forest drops that to 3.45 megawatts, a 25% improvement. Every fold tells the same story: blue bar higher, light blue bar lower. A paired t-test confirms the gap is real. P equals 0.0008. Why the forest wins? One straight plane can only tilt. It can't follow the slight plateau we saw above 30 degrees or the way vacuum and temperature interact. 200 small decision trees can each carve their own region, and averaging them keeps noise down. Note the tiny plus-minus 0.04 spread. Verdict: random forest is our champion. Now let's freeze that model, fit it on the full 80% training data, and see how it performs on the hidden test set. Now for the model's final exam, the 1,914 rows we never let it see. Results: root mean squared error, 3.48 megawatts. Mean absolute error, 3.12 megawatts. R squared, 0.93. The plant's average load is 454 megawatts, so that RMSE is only 0.76% of typical output. In the scatter plot, every dot represents an hour. Notice how tightly they cluster along the 45-degree perfect prediction line. No widening funnel, no systematic bias at low or high load. Before we open the hood to see why the model works, let's spend a couple of seconds in the notebook so you can verify these numbers at the source. Here's cell 5. It runs 5-fold cross-validation on both algorithms. You can see linear regression averaging 4.57 and random forest 3.45, exactly the bars on slide 4. Now cell 6. We fit the random forest on the full 80% training slice and print the holdout metrics: 3.48 RMSE, 3.12 MAE, R squared 0.93, the same figures you just heard. With the numbers confirmed, let's jump back to the slides and find out which features drive the model. Permutation importance on the test set shows temperature plus vacuum explain about 80% of prediction power. A partial dependence curve indicates each 1 degree rise trims roughly 0.7 megawatts. Summary: random forest, 200 trees. RMSE 3.48 megawatts. R squared 0.93. Data from Tufekci 2014. Code and scikit-learn. This completes the Duke University assignment. Thanks for watching.